welcome the first speaker, Professor Rama Govindarajan. She's a faculty at the International Center for Theoretical Sciences, TIFR, Bangalore, India. She is currently a member of editorial board for the physical review fluids. She is known for her work on flow instabilities, cloud fluid dynamics, and the combined dynamics of deformable solids and fluids. So I welcome the speaker. The floor is yours.
Thank you, Vagesh, and a very happy birthday to you, Bala, in advance. It's a big honor to be a part of your birthday celebrations. I've known Bala for some decades now, so I always think of him as this very young guy. So he's still very young at 60. So happy birthday, Bala.
Thank you, Rama. Thank you very much.
So today's talk is about surface tension as a destabilizer in 2D, and it's mainly the work of Rashmi Ramadugu as part of her PhD thesis, which is getting ready. And she is a joint student of Prasad Perlekar at IIT Hyderabad, TIFR Hyderabad, and me. So there's also, this work is based on older work done with Harish Dikshit. So I will be referring to that older work also quite a bit. Okay, so I'm going to talk about two standard dogmas and then talk about what happens to these dogmas in the neighborhood of a vortex. So here is the Navier-Stokes equation, and we're going to talk about incompressible flow today, but density can vary, like it could be oil and water or, two different fluids, or yeah, that's basically what we're going to talk about. And here's the Navier-Stokes equation in general with the surface tension force and the gravity force. Now, normally, like if the density variations, delta rho, overall are very, very small compared to some, typical density in the flow rho naught, and you define an Atwood number like this, and you say that if you say that the Atwood number is much, much, much less than 1, that means delta rho is much, much smaller than rho naught. Normally, you just make this thing called the Boussinesq approximation, and you say that I'm going to replace rho everywhere by rho naught except in the gravity term. Like over here, I'll recognize that there is a variation in density. And this is normally the Boussinesq approximation. Now, the Boussinesq approximation automatically neglects centrifugal effects. So all effects here are neglected. And we showed long ago that in the neighborhood of a vortex, in the neighborhood of a vortex, there is something like the centrifugal acceleration can be written down by gamma square by r cube, where gamma is the circulation of the vortex and r is any radial distance. So this force depends on how far you are from the vortex. So suppose you're quite near the vortex and it's quite a strong vortex, then this non-dimensional number can be order 1 or more, and this makes it such that, and you can think of this as some kind of Froude number. If this number is order 1 or more, then you cannot make the Boussinesq approximation. So in addition to Atwood being very small, you need another condition that this number should also be much less than 1 in order to make the Boussinesq approximation. So this is one point, like normally people make the Boussinesq approximation when Atwood is much less than 1, but we have to talk about whether we are in the neighborhood of a pretty reasonably strong vortex, not unusually strong, but reasonably strong or not. The second dogma, like we always talk about surface tension stabilizing, but of course we know that in the Rayleigh plateau instability, it's an instability driven by surface tension. The difference here is that this is in 3D, and what we're going to talk about today is in 2D. So we know that surface tension can destabilize because surface tension hates surface area. It tries to minimize surface area, and bizarre though it may seem, by taking a cylinder of fluid and perturbing it, you can actually reduce its surface area in 3D. You can do this simple calculation. And we're going to talk about another thing where surface tension indulges in vorticity generation, and therefore it creates an instability. Okay, So now, like, why are we talking about the vicinity of a vortex? And what are we talking about it in the context of? So let's just look at a simple picture of decaying two-dimensional turbulence at a particular time. The turbulence organizes vorticity. This is positive and negative vorticity shown by red and blue in this figure. It organizes vorticity into these near circular patches. And though some of them are distorted, a lot of them are near circular. And if you, in fact, like we've taken this vortex 1 and 2, two typical vortices, and plotted their vorticity profiles as a function of x and y, and you see that these profiles are very, very close to Gaussian. Now, a Gaussian vortex, Gaussian profile vortex is called a Lamboscene vortex, and it's an exact solution of the Navier Stokes with an increasing, radius and decreasing maximum as a function of time. So you can see that 2D turbulence is like can be thought of as a collection of Lamboscene vortices of different strengths in the flow. Now add to that like interfaces. So think of it as 2D turbulence of two immiscible fluids. So you can get interfaces of different shapes along with this vorticity. And so what we decided we'll study is the building block of this thing, which is basically a Lamboscene vortex. And we took the simplest interface, namely a straight line, just to study it analytically. So we're going to study this building block analytically. We can also have two different densities on either side of the interfaces. So it could be two immiscible fluids of different densities, and there is a surface tension sigma on the interface. So we will first study this building block. Now, in this building block, there are two mechanisms for vorticity creation. Already you have one Lamboscene vortex over here. I hope you can see my cursor.
Yes, we can.
Okay, thank you. So like this is a Lamboscene vortex and this is a general interface. We're going to talk about vorticity creation along this interface. So if this interface was not at all vertical at time equal to 0, it's going to become vertical just because there's a strong vortex in the vicinity. And we're going to see how. So we rewrite the Navier-Stokes equation in terms of the vorticity equation. And we write, so omega is now the vorticity. And there's like two generators for vorticity. One is del cross F sigma, where F sigma is the surface tension force, which is, acting normal to the interface at any time. And if the interface is, some generically curved interface, the curl of this is in general not going to be 0. And you can get vorticity generation due to surface tension. This is one central point I want to make. And this term goes to 0 because the density is also jumping across the interface and the surface tension, they both act in the same direction. The other creation of vorticity is due to this term called Baroclinic Torque, and we will come to that. So even in the inviscid case, so like our mechanism is actually inviscid. If we understand the inviscid problem, we've understood the problem. Viscosity doesn't do too much to change the answer qualitatively. So like we do have a Reynolds number because we have run, our simulations at finite Reynolds number. We've done 2D simulations at finite Reynolds number. But we're going to do the analytical work at infinite Reynolds number, and they're going to qualitatively give the same answer because there's no particular way in this problem in which this term acts as a singular perturbation. So we can happily study inviscid and understand about high Reynolds number. The other non-dimensional number here, apart from the Atwood, which I explained earlier, is the Weber number. So the Weber number is defined based on the a typical velocity of the vortex itself and a typical velocity, a typical size, a kind of core size of the vortex itself. And this, we can just remember that as the Weber number goes towards infinity, the surface tension goes towards 0. So these are the important parameters we're going to talk about. Now, what happens to this building block that we talked about? We start at 0 time with something, it could be a point vortex, it could be a Lamboscene vortex. So here we are studying about a Lamboscene vortex. And if we start out with a straight interface and this vortex is going round and round, the vortex is going to wrap this interface into a spiral. And we can actually write down this spiral with, a few lines of algebra. And, it has it gets tighter and tighter wrapped as time goes on. And this is, at any instant, it is describable by an Archimedean class of spirals, which is called a Litous spiral. So this interface exactly is a Litous spiral at a given time. So the only thing is the way it wraps around keeps changing with time. Now, the important thing here is that the spiral is not a circle. And because the spiral is not a circle, so there's one thing I want to explain here, which is that if you have, this vortex, the pressure gradient due to the vortex, the centrifugal thing, is along the radial direction. The pressure gradient is along the radial direction, and the density gradient is perpendicular to the interface. So these two need not in general be collinear, and so you can get vorticity generation. And in particular for a spiral, it is not collinear. So you have the pressure gradient in that direction and the density gradient in this direction for this general interface, and therefore you have baroclinic torque creation. And exactly on the interface, it's basically a delta function generation of vorticity. So you're going to get that. So then in steady inviscid flow, we can actually write that down. And that's why I gave you in the first slide an argument for, basically that the vortex can be thought of as producing a radial gravity. And the thing that immediately follows is, just like, when you have a regular Rayleigh Benard or Rayleigh-Taylor instability, if you have light above heavy, then baroclinic torque is created to stabilize it. But if you have heavy over light, then baroclinic torque can destabilize it. Similarly, you have heavy inside light can be destabilizing, and heavy outside light can be stabilizing. So that's basically the same argument here. So you have a radial force instead of a gravity acting this way. So that is a reason for instability already. And in a spiral, you get alternating density jumps. So every alternating one is stabilizing and the other one is destabilizing. Now, the normal dogma about surface tension that we are always taught is that surface tension does very little to long waves. So if you have a very long wave like this, then, by reducing the surface area or making the interface a straight line, you gain very little. Whereas if you have a very, very jagged interface, then surface tension will like to make it into a straight line. Therefore, it stabilizes high wave numbers where wave number is k and does very little to small wave numbers. This is the basic dogma. But that's going to work differently in our case. Of course, it will still do this, but it will compete against itself. So how does that work? So that's because the vortices themselves distort the interface. We saw that a straight interface is quickly wrapped into a spiral. Namely, the interface is made longer by the action of vorticity. So the interface is made longer, and surface tension doesn't like that, but it can't just reduce it like this. It sometimes, and because it generates vorticity along the interface in this fashion, because it generates this vorticity, it can't merely reduce the surface area. It can actually generate this instability via generating vorticity. So once you have vorticity on the interface, you can think of it as a velocity jump across the interface. So any vorticity on the interface is a velocity jump across the interface, and therefore the interface is immediately subject to Kelvin-Helmholtz instability. Any velocity jump across an interface is Kelvin-Helmholtz unstable. So here is Rashmi's simulation. You see that at 0 time, we started with a Lamboscene vortex and a straight interface. So this is density and this is vorticity. And after some time t, it wraps itself perfectly into a Litous spiral that we could write down, except within the core, where also we know what it does. So we can actually write down the form analytically within the core itself. So then like we can look at it analytically in the inviscid limit, well inside the core and well outside the core. We can get like very, very simple answers. In fact, we can solve this problem everywhere for inviscid flow, which we have done. But I'll just talk about two limits here, the well inside the core and well outside the core. Now, well inside the core, there is a velocity jump entirely due to surface tension. D is just a constant given by this number, and Q here is just R over the critical core size of the vortex, the whole square. So Q is just a square of the non-dimensional distance from the center. So like when Q is much, much less than 1, that means when you're well within the core, you get a velocity jump across the interface primarily due to surface tension, and it goes up as square of time. So like it's quadratic in time. That's the interesting part. So like the message here is that sometime or other, this velocity jump is going to become powerful enough that it can generate Kelvin-Helmholtz instability of significant growth rate. That's the basic message. So surface tension inside the core can generate, instability at some time or other. And when it does that, it can mess with the vortex itself, and the whole vortex can commit harakiri in this way. The other thing is that at very, very large distances away from the core, you get still, velocity jump due to surface tension and due to the density jump. And one is quadratic in time, one is linear in time. And so you can see that there is velocity jump, and depending on the sign of this thing, you can get instability or stabilization on every alternate one. So like basically this one, if it's black to white, it will generate velocity jump of one kind, and white to black the other kind. That's this term. That's why there's a plus minus. It's like plus on one and minus on the other. Whereas surface tension always generates velocity jump of one sign. So long as together they are big enough, they can generate instability. So the density jump sometimes helps surface tension and sometimes acts against surface tension. Okay, so like, from simple arguments such as you can find in Chandrasekhar's book, you can write down like various growth rates, knowing the, if we look locally at, wave numbers which are smaller than the size that we're talking about. So like for an Atwood number of 0, let's first talk about density jump absent and only surface tension acting. So you can get a disturbance frequency and wave number in this way. Now, if this thing inside this square root sign is negative, you can get a growth rate because you'll get an imaginary part of this wave number. So then like what happens here is that if this number goes below 0, so how can it go below 0? It's when this velocity jump is big enough. So you now remember that the velocity jump itself was going up quadratically in time with surface tension, with the Weber number, the denominator, that means surface tension in the numerator. So higher the surface tension, better is this. So then like we just write that down here. And now well inside the core, we have this formula where you see surface tension competing against itself. Here is a positive term, stabilizing term, which is, the usual thing where it hates, very short wave disturbances, and it tries to stabilize them. K is the wave number, remember. So then like here it is trying to stabilize, and here it is trying to destabilize due to vorticity generation. And just staring at this tells me that at some time or other, this is going to win over that. And so that time is this. So everything, this flow becomes Kelvin-Helmholtz unstable inside the core. Namely, it's going to mess the vortex core at times greater than this quantity. Remember, D is just a constant. So this is a purely surface tension driven instability. We now do direct simulations for the same thing, Atwood number 0. So no density jumps to confuse us. And we've chosen like a, pretty strong Weber number to see like what happens to the single vortex. And so like we remember that the delta U goes up quadratically in time. We plotted it for 2 times all across the radius. Now, the interesting thing is that this form we derived for very, very small q, but it's pretty decent for q going all the way up to 1. And so you see that the simulations, the direct numerical simulations, which are given by the symbols, are pretty decently obeying this simple delta U that we have. And we know the form of that in the q direction. So like as along q, and knowing that, we see that it's doing a pretty good job. And here is a photo of that vorticity it's generated within the core. And this is at shorter time, and at longer time, like it just goes Kelvin-Helmholtz unstable, and then due to the action of viscosity, this newly generated vorticity peels off from the interface. So remember that even though you're going Kelvin-Helmholtz unstable, surface tension simply hates that, and at some time or other, it's going to make the interface straight. But then the vorticity thus generated is going to peel off. So even if the interfaces come back to this shape, there's vorticity peeling off. So we see that this mechanism is active. So well outside the core, don't look at this formula, it's too messy. But all I want to say is that the centrifugal Rayleigh-Taylor that I told you on alternate arms of the spiral happens, and the spiral Kelvin-Helmholtz happens in every arm. And in the intermediate region where it's not well outside the core or well inside the core, both these mechanisms become important. Namely, density is more important outside the core, surface tension is more important inside the core, and in the intermediate region, both are important. So then here's just simulations from our old work on this spiral Kelvin-Helmholtz and centrifugal Rayleigh-Taylor instability. And you see that the minute you put a density jump, instead of passively rolling up into a little spiral, you see this beautiful combination instability coming up. And if I can boast about it myself, it's pretty nice looking. And so let's look at some movies now with the new one, which is, just to make life easy, we take Atwood number to be 0 and put only surface tension, which we never had before. So this is pretty low surface tension because the Weber number is very big here. So you see, oops, the other one is playing first. So anyway, so you saw that when you have very low surface tension, it's basically a little spiral, and the vorticity, you can see some instability coming up, but nothing much in the time of our simulation. Whereas in this, very high surface tension case, we just chose a very high surface tension to make the story clean. It's basically the same mechanism that I described in the previous slide, where the interface is going shorter, but the vorticity is peeling off. And you see that out of nowhere, this instability came, namely out of surface tension, this instability came about. Now we look at a combination of density perturbation as well as this, and now the surface tension is low, so this is primarily a density driven instability, but within the core you see like some effect of the surface tension as well. So it's a little different from the pure density instability as we see, because inside the core the surface tension is the winner. And now we have high density contrast and high surface tension, just to show you that, how quickly this thing degenerates into, you started from something like one vortex and you saw 2D turbulence coming out. So now we quickly look at, so this is just a picture of what I already told you. We quickly look at 2D turbulent simulations. So what we did is we ran a single fluid simulation for some time to generate some vorticity initial condition. And we took some generic interface, like here it's flower shaped, but it's actually, sinusoidal perturbations on a circle. So then like we started out with this as our initial condition. And after some time, you see how the interface has been wrapped into these very thin structures at high Weber and fatter structures at lower Weber, namely higher surface tension. And you see like all this vorticity generation, which is exactly like as we predicted. We haven't done very quantitative things, but in the vicinity of one vortex, we can, pull out characteristics, times at which we can see this, and all of that falls into place, like the Weber number at which we expect it for a given time, all of that falls into place. So even here you see instability, the vortex generation due to this instability, and this is at Atwood number 0. So there's only surface tension which is generating all this vorticity out of nowhere only on the interface. So the vorticity follows the interface very well. And this instability has, become very, very strong at higher surface tension. And now basically, so like these are some other patterns just to show how, the vorticity sometimes peels off from the interface and it's, different. So then we just end this by looking at the energy spectrum. As the surface tension increases, this is the Weber number, you'll see that more and more small scales are being created. And I don't have time to talk about this, but the typical length scale of a blob agrees pretty well with the Hin's length scale. So this is basically what I wanted to say today. And here's the summary in front of you. And thanks for your attention.
Thank you, Professor Rama, for an interesting talk. We still have some time for a few questions.
So will people be asking the questions?
Yeah, I'm just seeing if somebody has raised a hand, or they can speak or write a question in the Q&A on the top.
Vagesh, can I ask a question?
Sure.
Rama, you talked about the role of density variation and also surface tension. What about viscosity difference between the two fluids? How would that affect? The reason I ask is some of these pictures for high Atwood number, the very last movie, it looks like a little bit like breaking waves breaking. You look at this spiral, the initial stages, it looks like a breaking wave quickly, really. The viscosity variation will also play a role. So I wondered what your thoughts on it.
Actually, that's a brilliant question. So like we know that viscosity variations do things to interfacial instabilities. So namely the Rayleigh plateau instability. When you have a viscosity contrast in addition to this, like the Rayleigh plateau is typically written down for inviscid, but when you put in a viscosity contrast in addition, it becomes the Rayleigh tomotica instability, where viscosity jump can actually increase or decrease the growth rate of this instability. But we haven't studied it in 2D. We've been focusing at very high Reynolds numbers, but even at those Reynolds numbers, if you have a significant contrast, I do expect something to happen there, Bala, along the lines of the Rayleigh tomotica.
Thank you, Rama.
Okay, any more questions? We still have room for one more question. Yeah, there is a question from the audience. Palas Kumar for Soya says, is the zero viscosity case is singular?
Palach, in this case, the zero viscosity case is not really singular because, typically singular perturbations come when you have, let's say, a wall. Typically, you need a singular layer or a boundary layer which creates this singularity. And in our case, that thing is not there because directly like vorticity gets created on the interface, and it's just a simple case of Kelvin Helmholtz. So just like the normal Kelvin Helmholtz, if you calculate it for an inviscid flow, you will get a pretty reasonable answer for a viscous flow. The same exact thing is going on. The same thing is going on here, so it's not acting as a singular perturbation. So like as I keep reducing the Reynolds number, viscosity will dissipate my instability a little bit. That's about it.
Okay. There can be more questions in the Q&A, but I think we can move to the next speaker.